Okay. Problem, and you'll probably appear on camera to some extent. We are starting problem number 4, the rowboat. The hardest part of all these momentum conservation problems is the part where you read the question and imagine what's happening and try to find a way to look at it where you see a conservation of momentum occurring. This imagination is hard to teach, but here's how you can build it. You can build it by reading and sketching, rereading and checking. So let's just read, and I'll show you one way to do this. Andrew and Chris are sitting in a rowboat. So there's a rowboat, there's Andrew and Chris at rest on the surface of a smooth lake. Okay, so I know they're not moving. I know the mass of the rowboat is 25 kilograms. Andrew is 80 and Chris is 90. This is not my official sketch. I'm just trying to imagine and form a picture in my mind of what this problem is describing. Now, oh, it looks like something's happening. If Chris jumps off the back of the rowboat, so maybe I should draw a picture with Chris jumped off the back of the rowboat with a velocity of, okay, I'm given his velocity. How fast, uh-oh, I bet there's a question coming. How fast will Andrew and the rowboat initially move? So, how fast will Andrew and the rowboat, okay? So, I haven't chosen system objects. I haven't selected initial and final states. But just by drawing this out, I'm getting some sense of this problem. To treat this as a conservation of momentum problem, it would be nice if I could find a number of objects and be able to put a number on their total momentum. If there's no unbalanced external interactions, not receiving any pushes or pulls that aren't balanced by other interactions, then I know the total momentum will be the same. So with my experienced eye, I can kind of see that Andrew, Chris, and boat might be a good choice for the system. Because at this moment, I know all of their masses and all of their velocities. So I just know that the total momentum in these 3 objects is 0. Over here, so if maybe this is going to work for an initial moment. Let's see what would happen if we call this the final moment. Well, since I know Chris's mass, I know I can find the final momentum of Chris. That's going to be a known quantity. Here's where you have to apply a little additional imagination. Why not simply treat Andrew and the rowboat as a single object? They're moving together. I know both of their masses. This is what I can see makes this a simple problem to approach. So if I call, I don't know the momentum of Andrew and the boat, but I know the mass of Andrew and the boat. That's the mass of Andrew plus the mass of the boat. So maybe let's skip. Let's put up a bar chart and see if this might be a productive way to work. So if we're considering Andrew and the boat together, then we'll have Andrew and the boat and Chris. Initial momentum of Chris, initial momentum of Andrew and the boat. Let's just make sure that nothing is changing the total momentum of the system. I have the earth is pulling down on these objects and the surface of the water is lifting them up. There doesn't appear to be anything outside the system making any changes to the total momentum of the system. So there's no unbalanced forces. The change is going to be 0. I know that the initial momentum of Chris is 0, not moving. And I know the initial momentum of Andrew and the boat is 0. Now, the final momentum of Chris is a known quantity. We haven't calculated it yet, but we know what it is. That means what? We've got 4 out of 5 bars. So if this is a known quantity, we know that that we're going to be able to find that out. So that means that the final momentum of Andrew and the boat, that's going to be a known quantity. Is that going to help us get toward our unknown quantity from the problem? Yes, sir, because the mass of Andrew and the boat is known. If we know that, we'll be able to solve for the velocity of Andrew and the boat. You with me? We haven't really done any calculations yet. We're just taking an inventory of what we know and what we can find out. Let's see if we can make this a little tidier. So here's our bar chart. Let's calculate some quantities. The final momentum of Chris is equal to the mass of Chris, 90 kilograms, times Chris's velocity. Wait a minute. I'm starting to do calculations. There's velocities involved. Let's go back and check our directions. Doesn't matter what I pick. Let's just call to the right to be the positive direction. That means that Chris's velocity is going to be positive. So let's go back to our calculation. Plus 6 meters per second. So Chris's final momentum comes out to be